Hey, Vlad here, devinside.com. Welcome to another video. In the previous video, we talked about algorithmic complexity, which was a prerequisite for this video. So our sets right now are struggling because they're implemented with a linear structure, right? And therefore the complexity for the most important operations are is linear, right? So today we're going to learn about trees, which are going to help us to achieve logarithmic complexity. So we have a lot of work to do, so let's just get started. All right, so we need to talk about trees, and therefore we're going to start with the drawing board. And a quick disclaimer, I don't like to make videos with mathematical backgrounds, not because I don't really understand it, because just like this is not what I'm passionate about. Like I'm passionate about like building big software systems and making sure that they stay scalable and so on and so on and so on. So as a disclaimer, I'm not going to teach you everything you need to know about trees over here. I can link a few links down in the description with a bunch of YouTube videos with like really beautiful graphics which explain trees in every possible aspect and detail. There are a bunch of different kinds of trees. They have different complexity and so on and so on and so on. So as always, I'm going to take the pragmatic approach, and I'm going to explain only the things that we really need to start writing some code. And we have a lot of code to write today, so let's just get to it. So what we have so far, we're working on sets, right? But we implemented them with just a single link between them. So you could sort of call them a single link set. So usually single links are being discussed with lists and not sets. But it's basically the same idea, right? So if you want to draw them, you basically draw rectangles like this with two things. So the first thing is going to be the element. So let's say we have a set of strings. So the first one is going to be the word hello, right? And then the second element is a link to another one of these rectangles, right? So you have another rectangle like here, and this is going to be world, right? And then you have another link to another rectangle. So the last rectangle is going to be just a rectangle with one of these dots, and this is the empty set. So we have been calling it empty, but usually sometimes it's called with nil, and nil I believe stands for nothing in Latin. But basically, like what we have written here is a what we write in Scala usually is a set of hello world. Now there's an order over here usually, which is why it's usually explained with lists. Sets don't have an order, and it's actually incorrect. Like sets don't guarantee an order, but the implementation still has an order, right? So this is our implementation right now. So if I were to jump into the code, which is something that I don't want to do now, we have basically a trait called set, right? And we have two implementations. We have an object empty, and we have an object, no, this one is a class actually, class non-empty, right? So non-empty, it has the element, right, which in this case is a string, right? So this is the element, hello and world, and it has a second parameter, which is other elements. I'm going to call it O elements, right, which is basically just a link to the other sets of strings, right, to this one, and this is the second element, right? So today we're going to learn how to make a tree out of this, which is a hierarchical data structure. And basically what we'll end up having here is not other elements, which we're going to have instead. We're going to have the right branch, and we're going to have the left branch, which we're going to have over here, right? So a non-empty version of the set is not going to have just two things. It's going to have three things, right? So this one is going to be the right one, for example, and it's going to have yet another one here, right, which is going to be a link to the left one, right? And it's going to be like this over here, same thing. It's going to have like two things, also like left and right, and so on and so on and so on. Now a better way to draw this would be with circles. So you just have a circle here, goes like this, goes like this. So this is the single link over here, and what we would have is another one here, another one here, another one here, and so on and so on and so on. So usually like this is drawn when it's flipped to the side. So our arrows go to the right. Now usually they go down, so you have something like this, right? Sometimes arrows are used, sometimes not arrows are used, you know. Okay, so let me remove all of that. Like, this is like the, you know, these are like the super fastly explained basics. Let me remove all of that. So again, a tree is a hierarchical data structure. It's basically like a regular tree. You know, a regular tree sort of looks like this, right? Oh my God, I'm drawing so badly. So this is like a regular tree in real life, and the trees that we have, they're sort of upside down, right? So let me remove this nonsense. So you start with a root node, and then it can have many children, right? And then they can have many children, and so on and so on and so on and so on and so on, right? So the popular trees that we're going to talk about today are binary trees. So binary trees, they have only two children, right? So we have a root, and it can have 0 children, it can have 1 child, it can have two children, but not more, right? And the same for these guys, right? So it goes on like this. It grows like binary because, you know, because the number of 2 is there, right? Like this, like this, like this, like that, right? So again, as I already mentioned, there is a lot of terminology in terms of trees. Like this one is called a root. The ones that don't have children, they're called leaves, right? So this one is a leaf, this one is a leaf, this one is a leaf, and so on and so on and so on. This tree, because it's, you know, there are layers, they have like depth and so on. This is sort of like a lazy lazy explanation of trees, right? So they have depth, and if the last layer is completely filled out, you know, if it's completely filled, then it's called a balanced tree, right? So if the last element was not there, then it's I believe it's called partially balanced or something, right? So if you sort of fill them from left to right, then it's like partially balanced, and if it's completely filled out, then it's called, like, I don't know, like fully balanced, or so on and so on and so on and so on. What's important though is, like, if you miss this one element, so if this one was not there, then it would not be even partially balanced, right? So you have to go them from left to right. But all of this doesn't really matter. And if you implement them, then occasionally you will have also, like for this one, you will have an empty here. And this is how we're going to do it over here, right? So even though these nodes don't really exist, in programming they will exist. Sometimes null is used for this, which is horrible. We're not going to do that. All right, so what is the benefit of this? Well, the thing is that if you remember our sets right now, so they look like this, right? Right. Okay, so there are elements in there. Let's say that there were numbers. Let's say it was like 1, 2, and there's no order. So this one is going to be 5, this one's going to be 7, this one is going to be 8, right? So you're inserting an element. Let's say that you're inserting an element 8, right? So what we have to do now is we have to basically make sure that the 8 does not exist. And in order to find the 8, we have to go through all of the elements. So the complexity is linear, right? We have to go through all of this, right, which is n times, which is 1, 2, 3, 4, 5 times, and we will end up rebuilding this entire set, right? Because replacing the last element in the single link scenario would mean that you have to go to this element, right, to this 7, and you have to say, okay, your link is not going here anymore, your link is going somewhere else. Now in this case we're inserting an 8, so we're actually going to end up not doing anything. But let's say we were inserting a 9, we'd have to go through all of the elements, right, and then insert over here another 9. Actually, let me draw it like this. Another 9. So basically we would need to change the link of the 8, but we're talking about immutable links, right? So we can't just change this element, right? So in order to change this one, you will end up recreating it. And if you recreate that, then you need to make sure that the 7 points to it, and then that this 5 points to it. And so basically you end up rebuilding the entire link. And what we'll end up having with trees is that we will end up rebuilding only one path. So for example, if we had a way to know that the element that we will want to insert, that it will be here, then what we need to rebuild is only this, right? Which is a way better algorithmic complexity. So over here we have 2 to the power of 1 minus 1 elements, which is 1. So the maximum number of elements that we have over here is 1. The maximum number of the elements over here is going to be 2. And it's 2 because it's 2 to the power of 2 minus 1. It's actually 3. So what I mean is that this is the number of elements in the entire tree, right? So until here there's 1, and until here there's 3, right? Over here we have 2 to the power of 3 minus 1, which is 7, right? So if you count that, 1, 2, 3, 4, 5, 6, 7, and you keep going like this, 2 to the power of 4 minus 1. So it's always the same formula. Hold on. So we have 1, 2, 3, 4, 5, and we have the 6. and we have the 7 over here, and we have the 8. So 8 plus 7 is 15. Okay, so by the way, this is the depth. Like, this is like a weird formula for the depth. So if you do 1 minus 1, this is the depth. So this is the depth of the tree, which is 0. If you take this, 2 minus 1 is 1. It's depth over here. 2 depths. 4. There's also height of the tree, but again, like, this is like way too much terminology that we're actually not gonna need today at all, right? But basically, what is happening is that the amount of elements it grows with the it grows with the exponential complexity, right? So you have 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. We can ignore the minus 1 for now, right? 2 to the power of 4, and so on and so on and so on. So let me draw like another tree over here. So as of right now, we have our sets that look like this, right? Which is also oh my god, what did I just do? Which is also a tree, but it's like a degenerate tree. It degenerated to a single linked set. I mean, usually you say list, but doesn't really matter. So it degenerated to that. So if you wanted to find that element, then the complexity would be n, right? To find that element, for example, in order to add another one, right? It's going to be n. So what if we had another branch like this? Then it would be divided by 2, right? Now 2 is just a constant, so we can pretty much ignore it, right? So the complexity will still be linear. You know, you have to go this way and you have to go this one. But if you keep doing that, right? If we keep doing this with every node like this, then you'll keep dividing this complexity by 2 again. You divide it by 2, you divide it by 2, you divide it by 2, right? So you end up, like, because of this, you end up with a logarithmic complexity, which is really, really good, because you have to, reconstructing one path has a logarithmic complexity. Okay, so these are binary trees. Let me remove everything. The next cool thing about trees is that you can have binary search trees. So I'm gonna say BST. The binary search tree looks exactly the same as it looked before, right? Like this, like this, like this. But there is a fixed algorithm of inserting elements or of finding elements. So basically, every time you insert the element, there will be a function that you can call on your element, which will give you a number back, right? So in our case, we're gonna use hash codes. Like, usually when this is explained, numbers are used, but I believe that this is confusing. Like, imagine that this was a binary search tree for strings, right? So over here will be hello, over here will be world, so on and so on and so on. Every one of these nodes has a string. So you can call hash code on the string, and you will get a number back, right? So there will be some number. Let's say that this was number 5, and this was a number I don't know, 1. This was a number I don't know, minus 10. And this one would be a number 3. This one would be a number, I don't know, 9. This one would be a number, I don't know, 7. And this one would be a number 12. So what I just did was not just picking random numbers. I mean, they were a little bit random, but they fulfill a very certain property. In fact, let me redraw this because you can't really read this. So let's do 5, 1, 9, negative 10. You have 3, you have 7, and you have 12. Okay, so just ignore this crap. Okay, so all of these numbers, they have a so-called partial order, right? So they're ordered, but not completely. They're ordered partially, and the ordering works like this. So if you have a number over here, then every number that is on the left, literally every number, everything over here, has to be smaller, or in our case, it's going to be smaller or equal 5, right? So 1 smaller than 5, 3 smaller than 5, negative 10 is smaller than 5, and everything that is on the right is going to be bigger. Right, everything over here is bigger than 5, and the same story repeats for every node. So if you take this 1, everything on the left is smaller than the 1, and everything on the right is bigger than the 1. You take this 9, everything on the left is smaller than the 9, everything on the right is bigger than the 9. So this gives us really beautiful traversing properties. For example, inserting an element. Let's say you want to insert an element. My God. Let's say you wanted to insert a string called world. Right, and then let's say that the hash code. So if you do dot hash code of world is going to be some number. Let's say that the number is 13, right? Then you want to insert this into this tree. So you will say, okay, is 13 smaller than 5? You'll say no. Okay, so we have to go to the right tree. So is 13 smaller than 9? No, so we have to go to the right tree. Is 13 smaller than 12? No, we have to go to the right tree. Oh, the right tree is empty. Okay, therefore we're going to insert the 13 over here. So finding this path doesn't require us to walk through every element, right? So we only need to walk through just a few elements. Right, this is where logarithmic complexity comes into place. The same for removing the element. You need to find it first and then remove. The same for checking if the element contains. For example, you're looking for if the word hello is inside of it. You just calculate the hash code. The hash code is going to be, I don't know, 3, or let's say 1. Right? So you just go in here and you say, okay, is 1 smaller than 5? Yes. Then go look for it left. Is it over here? Yes, it is over here, right? So you just found it without like looking at this, right? And so on and so on and so on. So you don't have to walk the entire line. You just have to walk, one part of the path, right, to find it. Okay, so this is all the benefits, and I believe that this is actually all you need to understand about trees. One tiny thing though that I will also add is that you get this logarithmic complexity only in the average case, because you can't, like in this case, if you don't add some extra code that makes sure that this tree is balanced, then you cannot guarantee that this logarithmic complexity will always work out, right? So you cannot guarantee this logarithmic complexity is the complexity of the worst case scenario, because if you, for example, if you insert elements in order, right? So if you have a bunch of words, like you say 5 words, and the hash code of these 5 words just happens to be ordered, right? So let's say it's 1, 2, 3, 4, 5. Then adding them into the tree is going to be like this. Okay, so the tree is empty, so we're just going to do 1. Then we're going to add up a 2. Okay, is 2 bigger than 1? Yes. Then add it over here. Then we're going to end up as 3. Okay, is 3 is bigger than 1? 3 is bigger than 2, so over here. So just going to go like this, like this, like this, and it's going to degenerate to a list again, and then the complexity is going to be linear. Okay, so today what we're going to implement is a tree that is not going to be always balanced. So the logarithmic complexity we will have is will only be in the average case scenario, right? So just something to keep in mind. Maybe in the future videos we're actually going to add some balancing to the tree, or maybe we'll actually implement a so-called red-black tree, which is going to always have the logarithmic complexity even in the worst case scenario. All right, let's start writing some code. All right, so as always, we're in the Ubuntu virtual machine, and we have Sublime at the top and the regular terminal at the bottom, which runs SBT, which runs our test for us every time we save the file, if I did that. However, today we're not going to do that. We're actually going to start looking at our code coverage. So if you remember, in our build file, we have an alias called test-c, which is going to do clean coverage test and coverage report. What the hell is going on? Somebody's killing children out there. Anyway, so as of right now, we're running our tests. So we cleaned the project, we're running our tests, and we're calculating the coverage report. And I don't know why, but sometimes it takes forever. All right, there we go. So if I press enter, then we'll actually see, okay, let me press enter again. So we have a written HTML coverage report at this link. So if I double click on that, right click, I copy that. I'm going to go to a separate workspace over here. I'm going to open Firefox, or you can open Chrome or whatever, any browser, just paste that over there. Oh, it had a paste and go. That was interesting. I've never seen this before. Paste and go. Ooh, that's cool. All right, so why are we doing this today? Today I'm going to show you that even though our API is not going to change, every time you're changing the implementation, you have to keep an eye on the code coverage. Seriously, what's going on? You have to keep an eye on the code coverage, because depending on the implementation, it might actually go down and up, right? So we're actually going to see this by the end of this video. So what's happening over here? So if we go to set what is red, we're going to see, remember these pattern matching that we disabled because pattern matching is just a syntactic sugar over equality, and equality is expensive for sets, so we turned it off, right? So we have a bunch of private methods that are just throwing this exception. Okay, so we haven't tested this, so and I actually don't really want to test this because we're actually going to throw out like a part of it today, because we're going to have our trees. So we're just going to turn it off. So if I go over here, if I go to the bottom, and by the way, everything is folded here. Let me unfold it, because in the previous video we folded it and I left it like this. Okay, code folding, unfold all. Okay, there we go. So if I go down to the bottom, okay, that's too much over here. So they're all over here. So what we can do is we can, and I'm actually going to copy paste stuff because this video might end up being really long, and I want to get through this a bit faster. So all of these pattern matches, like over here, for example, this one like this one like that, it's going to be on again. This one, all of these unapplies, enter it over here, off, on. The entire apply, actually, we're really, sorry, the entire, I thought it was this one, I meant this one. So the entire pattern mesh not supported, we actually don't need to measure coverage for it. So we have off over here, we have on over here. Right, so let's just do this thing again. Let's do test C, and if it takes too long, then I'm going to cut it out. But in this case, it seems like it was actually kind of fast. Oh no, it's still not done compiling one file. Okay, there we go. Okay, 97.94. I think it got better. Let's go refresh. What's happening? Come on, refresh. There we go. Okay, so all of that stuff went away. So we can go back to all packages and see. Okay, so we have only, so we're done with sets. So we go to foldable factory. Oh, we forgot to test filter not. So let's just add a few tests for filter not. All right, so let me just close the build file, and over here in our test, let's just look for intersection. Okay, this is intersection. So we have our filter here. We should also add filter not. So I'm just going to copy these, paste them all over here, filter not. Right, so if we have filter not, because we're working with an empty set, whatever we're doing here, it will remain an empty set. So in fact, just having that is not going to be enough to increase our code coverage, I believe. Let's just see. I'll scroll down over here a little bit. All right, 91.97. So I believe it actually increased a little bit, right? So it says, oh, okay, so we're calling filter, but we're not calling this. So because we're working with empty sets, so we actually need to go to this one and do something proper with it. Okay, so what we're gonna do is I'm gonna copy these. These are the ones that are doing the intersection, which is basically the same as filter. In fact, let's switch to continuous testing. Okay, so the filter works like this, and we're gonna do the same thing for filter not, but again, like in this case, it's still an empty set. So it's still not gonna improve our code coverage, right? Because it's an empty set, like all of these will remain false. Okay. The interesting part is actually over here. So if we intersection and the filter should be the same over here, but this is the point where the filter not is going to change. Right over here, the filter not on a non-empty set. Hold on, like this, and over here should be an empty set. Oops, like that, like that, like that, like that. Then these ones should be switched to true. I know that this is a bit too fast. I'm just trying to save some time. You can look at it a bit later in the commit. In fact, we're going to have multiple commits in this video. Okay, so the tests are passing. Let's see if this is actually enough for our code coverage. All right, 100%. That's cool. All right, so 100%. Everything is fine. Everything is green. Awesome. Let's go back to our code. So what I'm going to do now is actually I'm going to commit this code. So this is going to be. Let's just add everything just in case. Git commit -am. Okay, so this is video 9. Okay, I'm just gonna call it trees, and I'm gonna also have over here coverage. Right, so we're gonna have multiple commits today, and this is also what you should do in production. So if you're, if you set up to work on some task, but you notice, okay, you need to refactor something over here, or you need to write some tests, split these commits. This way, it will be much easier for code reviews or just in general to see what the hell happened. Okay, so we're gonna have this commit. Okay, now all of these dots should disappear. I'm not going to push it now. I'm going to push it by the end of this video. Okay, so all these dots disappeared. So what we're going to do now is we're actually going to refactor our sets a little bit, which is going to make introducing of the trees a bit more easy. Okay, so the first thing that we're going to do is, actually, I'm not going to touch the test anymore. So I'm just going to do that so that we see only what is happening. Come on. There we go. Okay, so we have only our sets. I'm gonna go back into SBT. I'm gonna keep running the test, but I'm not gonna touch the test anymore today, I believe. Actually, a bit later I will. It doesn't really matter. Okay, so let's just keep running the test. So remember, because we disabled this pattern matching, and at some point I said that I don't want to distribute the implementation between this. Hold on. So remember, I said that I don't want to distribute the implementation between this non-empty set and this empty set. So what I said that I want to have all the implementation over here. I changed my mind because I actually really don't like these other elements of throw exception things. Okay, so what we're going to do is we're going to try to get rid of this. Okay, so I'm not going to comment this out now. What I'm going to do is I'm going to look at a method called sample. Okay, I'm just going to copy that, and I'm going to say that it's going to be an abstract method now, like this. Okay, sorry, like this. Okay, so and then I'm going to go to non-empty. right? I'm going to paste that in. I'm going to say that this is a final override def empty, def sample, okay? And okay, so this is not empty, right? So this is not the case where it's empty. So I'm just going to do this sum of, and the element is actually here now, so it's actually going to compile some element. And in case of empty, over here, let's go add it over here. All right, so again, it's going to be a final override def sample, and in this case, it's just going to be none. Right, so basically I just distributed the implementation. So in case of empty, I'm just going to say none, and in case of non-empty, I'm just going to say some element. This is exactly what the implementation was doing before. If I paste it over here, here, this is exactly what it was doing before. In the case of empty, it's just going to return none, otherwise it's going to return some. Okay, so let's have this. Let's see if it still works. All right, okay, so in the case of empty, the element doesn't exist, so we can say that this is an option of nothing. All right, and come on. Why does it need so long to compile? Okay, there we go. Okay, so it's green. So let's just keep going with this. Okay, so we're also doing the same thing with is a singleton. So again, so let's just copy it out, remove the final to make it abstract, remove all of this. Okay. Okay, so a singleton, let's do it in the empty case. Okay, over here it was above, let's paste it over here. So this is going to be a final override def is singleton, and an empty one cannot be a singleton, so we're just going to say false. And for the non-empty one, let's go here, add it over here, a singleton. We don't need to check that it's not empty anymore because it's already in the type, so we can remove that. And other elements, it's just called other elements now. So right, so other elements is empty. That's all that we need. So that should be fine now. All right, is singleton. Again, I really don't know why it takes so long to compile. Actually, hold on. Maybe actually, can we make it an abstract class? So instead of a sealed tray, let's do sealed abstract. Oh, come on, abstract class. Is that gonna work, or did I do something that prevents us from doing that? It's gonna work. Okay, I believe that sealed abstract, an abstract class, I believe has a better compilation performance than the trait. So tend to use abstract classes instead of traits. They also have a better binary compatibility. Anyway, let's keep going. So let's just double click here and then see where it's used. Oh, toString. All right, so let's just cut out the toString. Cut it out. We don't need to make it abstract because it's defined on any. Let's go to empty and let's put it over here. Okay, so final override def toString, and in the empty case, it's just that. Okay, so we can just remove all of this. Okay, so in case of an empty, this is how it's going to look like. And if it's not empty, over here, let's put it over here. Okay, so we don't need this if else anymore because it's not empty. So we're just going to have that. And I got rid of the curly brace. So let's introduce it again. So we have this val, and this is what we're returning. So what we're going to do now is actually we're going to factor out this val into a def. So I'm just going to cut it out, and therefore we're not going to need these. You're going to need these like that, like that, like that. And I'm just going to go here. I'm going to say private to this, and I'm going to insert it. So it's not going to be a val anymore. It's going to be a def, and it's going to get an input of a set of element. Okay, so we're just going to do this on the input like this. Okay, it's just a tiny refactoring. So now over here, when we're calling this, we actually have to call it with other elements like this. If I did everything correctly, I did not. Okay, element of throw exception is just called element now. There we go. Compiling. Is it faster than before? I don't know. Anyway, okay, everything passes. Okay, so let's see this one. Okay, fold seems to be the last one. Okay, fold is going to be the only exception, and it's going to become clear only in the next few videos. So fold, I'm not going to distribute fold to non-empty and empty. In fact, over here, I'm actually going to pattern match. So instead of having what we have over here, which is this, I'm just going to comment it out. We're actually going to, oops, I did not want to do that. So I'm just going to comment this out. Whole thing like this, and the implementation is going to look like this. We're just going to match on this, right? So if it's an empty, and again, we're not using the full-blown pattern matching, we're just matching on the type, right? Because we don't want to use the equality. Then we're going to return the seed, right? So this is basically this case. And otherwise, if it's a non-empty set, which is non-empty of element, right? Remember that type erasure doesn't apply here, right? The compiler needs to know that this is the same element over here, right? So it's actually not going to produce any warnings, okay? So over here, then we can just copy that, paste it over here. It's not going to be called other elements. It's going to be called, it's not going to be called other elements or throw exception. It's just going to be called other elements, which is called on a non-empty set, right? So it's going to be non-empty set dot other elements, seed, and over here, non-empty set dot element instead of element or throw exception. Okay, like this. Let's see, is everything still fine? Yes, everything is still fine. We can throw this out. And also what we're going to do is we're going to, so this is applying the function to the current element, right? So to this one. So what we're going to call it, we're just going to call it current result, and we're just going to have a val over here called current result with this value. So it's going to look like this. This is how our fold is going to look like. I don't want to have this empty line over here, and I believe this is all the refactorings that we need to finally get started implementing the trees. So now we can throw this out because I believe that it's not used anywhere anymore. All right. Okay. So I can exit again. I can exit SPT. I can go up like this, and I'm going to say this is not trees refactoring. In fact, like usually you should also check, like every time you refactor, you should also check that the coverage stayed 100%. In fact, you know what the hell? Let's actually do this. Let's here go back in. Let's go back in. In fact, I can do this SPT test C. Okay, it should work. So it's going to start SPT, and it's going to run this thing, and then it's going to exit. It should stay 100% though, because we just refactored some code. But again, sometimes it's actually happening that you're just refactoring some code, and then the coverage goes down. Okay, let's see. If it's going to say that it's 100%, then we don't even need to go to the browser. Yeah, it's 100%. Okay, so we're good. Okay, so let's actually do this, and we're going to say refactoring. All right, let's go back to SPT and keep running our tests like this. There we go. Okay, come on, compiling. All right, so the first thing that we're going to do is we're going to do some preparation. So the first thing is going to be other elements. So instead of having, because they're sort of on the right, we're going to call them right? So all of these, I'm going to call them right, except for these two. Oops. No, actually this one was also, okay. So other elements, split by comma space. What's it called? Other elements. It actually can be called just split by space, split by comma space. Okay, there we go. Except for this one, this actually needs to be right. Okay. So now everything should stay the same because I just renamed it to right. But just renaming it to right doesn't make it a tree. Okay, so what does make it a tree is that it has a right branch, but it also has a left branch, right? So the left branch is going to look exactly the same. Exactly the same as the right one, right? There we go. Okay, so now a bunch of things are not going to compile. So we actually need to start fixing things before we actually implement the actual the actual trees. Okay, let's just sort of make it compile. So for example, over here, when we're building the toString, we need to consider the right branch, and we also need to consider the left branch. So I'm just going to copy that. I'm going to paste it over here. Right, so we're going to do split by comma space the left one and the right one, right? Okay, so I'm just going to double click right, and then I'm going to see everywhere where it's used. So for example, a singleton means that the left one is empty and the right one is empty, right? So left is empty and the right. So basically everywhere, whatever we're doing to the right, we also have to do to the left one. Okay, let's also see where it's used. Okay, so it's used only in the fold. It's used only in the fold, and the fold is actually the easiest one to fix, which is kind of funny. So we're going to the right, so this is going to be the right result. So this is going to be a right result, okay? And what we're going to return is we're going to copy that, okay? I'm going to paste it over here. I'm going to replace right with left, and we're going to replace current result with right result. Okay, and that's it. This is actually the entire fold. Like fold, like when I started actually working on this, I thought that fold is going to be one of the most complicated ones, but it turns out that this is a very mechanical transformation. So basically, whatever you do, so you go like into the right branch, and then you go to the left, and so on and so on and so on. So this is very, very recursive. Unfortunately, it is not tail recursive because in terms of a tree, it doesn't actually just go down and it's done. It goes down and then it has to go a bit up. Right, so it has to go back, and because it has to go back, the recursive call is not in the tail position anymore. We're going to fix this in the next video, or maybe in the video after that. All right, so we have the fold and the add and remove. What is happening right now is that we're just using fold. All right, the problem with it is that if you keep using fold has a linear complexity because it has to touch every element. So if we keep using fold, it would work, right? But we will end up rebuilding the entire tree, which defeats the purpose. So we can't use fold. So I'm going to comment this out. And I'm going to comment that out. Right, and I'm just gonna throw an exception over here, so not implemented exception. Okay, so what I'm gonna do here is I'm gonna press enter. I'm gonna switch back to compiling, and I did not save the file yet, so it should still compile, right? But now I'm gonna save the file, and at least it should compile now, and unless I forgot something. Okay, everything compiles now, so now we can actually implement add and remove, and we can see that our tasks are still passing. So as of right now, let's just run our tests, and probably all of them are gonna fail. Oh, that's actually funny. 17 succeeded, even though we don't know how to add things and how to remove things, because probably 17 of them were working with the empty sets. Anyway, so most of them failed, obviously. Okay, so let's try to fix add. So the same as for fold, I will need to keep add and remove inside of this trait because, as I said, like in the next video or maybe in the video after that, we're gonna have to make them tail recursive, and the compiler will not be able to eliminate the tail calls if this implementation is spread out into the multiple subclasses, right? So I'm gonna have to keep the implementation inside of this file, and because of that, I'm gonna have to do the same pattern match. So I'm just gonna copy the pattern match, and let's start with add. I'm just gonna paste it over here. Let's move it to the right. Now the pattern match is the same, but what we're doing in every scenario is obviously not going to be the same, right? So what have we been doing in the case where it was empty? Well, in the case where it was empty, we're producing this non-empty set, right? So let's just produce it over here, the same non-empty set. So we had an input and we had other elements was empty. Well, other elements is now on the right. So what we need to do is we also need to produce an empty set on the left. Right, so basically, if you have an entirely empty set, the first step will be to create this non-empty thing. And by the way, we probably should rename this non-empty thing to a branch. Also, sometimes it's called a node. In graph theory, it's called nodes and edges. Right. So think of non-empty as a branch. So this is a branch with the element, and on the left it doesn't have anything, and on the right it also doesn't have anything. Okay. Let's start working on the non-empty set. So what if this is already an existing tree? Okay. So over here we need to distinguish things, right? So we need to say if the input, so that thing, if it is exactly the same as the element, right? So the element of this particular node, of this particular branch. If it's the same, then we leave our tree alone, right? Because remember, this is the sets, and the set they don't need this element again, right? The every element is distinctive. Okay, so in this case, we're just going to return the set that we have. So this is the same as over here, right? So if current equals, it's the same thing. Okay. Otherwise, and this is where the power of the trees come in. Remember, I said that we need to calculate the hash code. So if the input dot hash code, if it's less than or equal to this element hash code, don't forget hash code, right? Then we know that it has to go into the left branch, right? And otherwise it has to go into the left branch, right? So over here, add to the left. I'm going to call it subtree, and over here add to the right subtree. Let's implement to adding to the right subtree. So remember, with our list, we have to rebuild an entire list. Over here, we have to rebuild only this path, but we still need to rebuild things. So basically, rebuilding means constructing those non-empty nodes, right? So these branch nodes. So what we end up doing is we end up constructing a non-empty node, the same as we did over here. Remember, current and ACC. So we're constructing a non-empty, right? So on the left, things stay exactly the same. We just need to rebuild the right path, right? So on the left is going to be whatever was in the non-empty set in the left branch, right? Then the element stayed the same, non-empty set, dot element. Remember, because we're not touching this node, we just know that we need to add this input into the right branch. So what we need to do is we need to ask the right branch, not empty set, dot right branch. We just need to ask it to add this input. And that's it. This is going to be the recursive thing. So it's going to go back in and it's going to find, okay, should I still go right, or should I still go left, or should I still go right, or should I still go left, until it finds the empty node, and then it will actually add it. Okay, so until it finds the empty node, and this is where it will add this input. So this tiny empty node will be inserted somewhere at the bottom of the tree, right? And for the left one, it's going to be the same thing, but it's going to be flipped. So if I just duplicate this line, okay, whoops, sorry, I just wanted to remove that. So if I duplicate this line, all I need to do is, instead of adding to the right, I'm going to add it to the left, like this, and that is all. So if I run this now, if it compiles, and if it works, it doesn't compile. It doesn't like input. Why doesn't it like input? Not found value input. It's over there. Oh, I forgot to remove those question marks, like this. Okay, so now only 5 tests failed, and these should be the removal tests, right? If we go up, it's going to be, yeah, remove combo, remove blah 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 blah. So basically, remove is the problem. And for remove, we actually can copy paste the entire add, right? Because the pattern match is going to stay the same, and this logic is going to stay the same. It's just that what we're doing in those cases is going to be different, right? So let me throw out the fold over here. Let me actually throw out these comments. Throw this one out. Throw this one out. Okay. So okay, let me save it real quick. Okay, so I'm just going to copy that. Right? Okay, this time I'm not going to forget to remove the question marks. I'm going to paste it over here. Okay? And we need to do the same thing as over here. Right? Remember, so in the empty case, we return an empty one, right? And otherwise, if it's exactly the same, this is actually going to be the complicated part. This is going to be the part where we'll have to rebuild a branch, right? Because remember, we have a tree, but if you're removing an element somewhere at the bottom, easy, right? But if you're removing an element somewhere in the middle, we will end up rebuilding parts of the tree. So this is going to be the complicated part where we'll have to reconstruct parts of a tree. Okay, let's not do this now. So if we look at this one, removing an element, so over here, like, there's no removal here happening, right? It's just asking other elements, other subtrees to remove. So basically, we just need to replace add with remove, and the code stays exactly the same, right? So if you haven't found the element yet, you just keep asking your children to remove. You just need to know, are you going to go left or are you going to go right? Okay, so once you understand how to implement this part, it's going to be very, very simple. But before you understand, you actually need quite a bit of graphical representation of this. So let me draw a tree, like a random tree. Okay, I'm gonna have like big circles over here, right? Like that. Let's actually go one layer more. By the way, trees are, they're very recursive. They're very complicated. So just watching this video is never going to be enough. You really have to try it on your own until it sort of clicks in your head. And even then, because it's such an involved topic, if this is not something that you do every day, I don't know, a few months later, you're gonna forget it, right? So just one of those things: use it or lose it. All right, so let's say that you want to remove this node. Now, removing this node doesn't mean that you remove this entire tree, right? You're just removing this node, so you have to relink these ones over here, right? So let's have an example. So let's say that we have a 10 over here, right? Which means that over here it has to be something that is bigger than 10. Let's do 20. So let's say that we want to remove the 20, right? So something on the left over here has to be smaller than 20 but bigger than 10. So let's do a 15 over here, and something on the right is going to have something bigger than 20, so it's 25. I'm not going to go further down. It doesn't really matter. Actually, let's do this. Okay, so over here, let's do 12 because it still has to be larger than 10. Over here, it's going to be 17. Over here, it's going to be 23. Over here, it's going to be 27. Okay, so what we're going to have to do is we will need to move the 15 up over here. right? And we do this by reconstructing the node with the 10. Okay, so we take the node with the 10, and then we say that on the right it's going to be this node with 15, right? And it's going to have its own nodes, 12 and 17, right? So this stays basically the same, right? So this is the first part. So we're just going to say, okay, the 10 has this entire left tree on its right, right? And if you look at the numbers, everything is still fine, right? So 15 is greater than 10, 12 is less than 15 and is bigger than 10, 17 is bigger than 15 and is bigger than 10, right? So everything is fine, right? But now you have to say, okay, to this tree, which was on the left, remember this part, this was on the left, right? We need to add this entire tree. So basically, we just need to add everything from that tree to the left. So we're just going to go them one by one. We're going to say, okay, add the 25, and it's going to say, okay, 25 should go over here, right? And then we're going to say, okay, add the 23. So it's going to go here, add the 23 over here. And I'm going to say, okay, add the 27. Well, the 27 is over there, right? So we're taking whatever is on the left, union whatever is on the right. And this is the entire implementation, right? So you just change a few pointers and that's it. But you can't really change them because they're mutable, right? So you have to reconstruct that part of the tree. All right, so all we need to do is we need to take this non-empty set, whatever is on the left, as I said, and all we need to do is we need to say union non-empty set, right? And that's it, right? So we're just taking the left one and we're uniting it with the right tree, right? The same as I just drew. Okay, so let's throw this out. Let's see if it compiles and if the tests are running. If the tests are green, and they should be green. Yes, they are. Now we're almost done with the video. It's just that a few things are sort of missing. Now we have a fast insertion, logarithmic insertion, at least in the average case scenario. We have the logarithmic removal, right? But what about contains? Remember, contains. If you know which path to go, then you should have the logarithmic complexity. Unfortunately, in our case, our contains is implemented by foldable, remember? So we don't have contains anywhere here. So apply calls contains, but contains is actually implemented in foldable. I just pressed the default will be F12. I relinked it to Control B, which is go to definition. So it just went to definition of contains, which is over here, and we made it final. Remember, this is one of those things that you end up having with a top-down design, is that you have to predict like all of these possibilities, which is why I prefer to start always with a bottom-up design. So what I'm going to do is I'm going to say, okay, it's not final anymore. People should be able to override it, right? So I'm just going to copy. I don't need the implementation. I'm just going to copy that. I'm going to go back to our sets, and I'm going to put it over here. It's going to be a final override. Final override def contains, okay, and the implementation will be the same as add and the same as remove. I mean, the pattern match and all of these cases. In fact, you could also refactor them into one method, but I'm not going to do it because I know that we're going to revamp them in the future with tail recursive implementation something. Okay, so we have the same thing, but let's just throw the actual results of the branches. Okay, so let's have an empty here. Okay, an empty line here. Okay, so what if it's an empty set? Well, the contains is just going to say false. Okay, well, what if it's a non-empty set and we actually found the element? Well, if we found the element, then contains is true. Okay, what if it's in the left part of the tree? Well, if it's in the left part of the tree, then let's just ask the left part of the tree. Contains input, and the same thing for the right. If it's in the right one, well, let's just ask the right one, and that's it. It's very, very, very straightforward. Like once you actually understood the how the trees are being built, this is actually really straightforward. If it's empty, then it's false. If you found the element, then it's true. Otherwise, just ask left branch, and otherwise ask the right branch, depending on the hash code. By the way, this whole dependence on the hash code and this value of immutability, this is like one of those things. Every time you have sets are designed for data structures, right? So if you have a data structure that is mutable and you have the hash code that is dependent on this mutability, right, on the fields, that what you might have happening is that when you're inserting, the hash code was like this, so it was positioned into that part of the tree, but then you change this data structure, right? If it's mutable, you change this data structure, hash code changes, and you're asking the set, hey, does it contain my element? And it's going to try to look for it in the wrong part of the tree, and it's not going to find it anymore, right? So this is why, this is one of the values of immutability. It just makes more sense. It just makes your life easier. Also notice that contains is not tail recursive, the same as fold is not tail recursive. In fact, let's remove this. Contains is not tail recursive, fold is not tail recursive, add is not tail recursive, and remove is not tail recursive. They are all not tail recursive. And in fact, if we were balancing our trees, this would happen during the insertion time and during the removal time. We basically would say, okay, is it too unbalanced? Let's balance it, right? We're not going to implement it today. Maybe we'll never implement it. Actually, I haven't decided yet if we're going to implement it yet. So anyway, if you're balancing your trees, then you actually don't need the tail recursive implementations, because they're going to work like this in such a way that, because remember, you're only touching like one path, and one path is going to be really, really tiny, right? If the tree is huge, the path is still going to be really, really small. This is the beauty of those trees, right? So you might end up like almost never needing tail recursive implementation. But just for fun, we're going to implement them in the future videos. Okay, so as of right now, let's see if we actually have our test coverage still. It should go down a little bit. All right, it's actually horrible now. So let's go see. Let's go see. This is exactly why I made sure that it was up to 100%. So that you see that that it depends on the implementation, even though the API did not change. We did not change the tests at all. We didn't touch them at all. But now we will end up adding a few tests. Okay, so if we go to foldable, obviously nothing tests the contains anymore because we just overrode it. Okay, and if we go to set, then we're going to see that when we're removing, we're not actually testing this particular case, where what we need to remove is on the right branch. So we're going to have to add a test for this. And it seems like that's all, but it turns out that there actually can be a bug over here. I'm going to show this to you in a few minutes, but the tests are not going to notice. So we actually have one test missing for the toString. All right, so let's first add the test for the remove. It should be fast. Basically, all we need to do is we need to make sure that our set is not only big enough, but that the elements are inserted to the right. The beauty of integers is that the hash code of an integer is exactly the value of that integer. So if we just add 1, 2, 3, it will create a tree which will be linear, right? So it's going to have a 1, and the 2 is going to be on the right, and the 3 is also going to be on the right. And therefore, if we ask it to remove the 3, it will have to go over here. Let's just do that. So let's find the set suite. Let's find remove. All right, remove. So this is the last one for the removes. Okay, so okay, remove should remove elements from the right part of the tree. Let's say also should also remove elements from the right part of the tree. Okay, so if you have a set of 1, 2, 3, then remove 3 should be set of 1, 2. Okay, so this test should still pass. Okay, and let's test the coverage. I hope that it's enough, actually. It's in the right part. Did it change? Okay, it did change, but now we're not in the left one. Okay, so what's happening is that we're generating random inputs. We're generating random inputs for our sets, and therefore sometimes our tests are flaky, right? So sometimes they're here and sometimes they're there. So if I just run it again, all right, so if I do this, maybe, no, it's still the same. All right, so let's just also do, let's just say remove should remove elements from both sides of the tree. Yeah, that's better. Okay, so we have 1, 2, 3. So if we actually do set of 1, and if we go down, right? So if you go to minus, let's not have this 0 so that it looks sort of symmetric. So we have 1, minus 2, minus 3, and negative. Sorry. So if we remove the negative 3, then it should go into the left branch. It should be set of 1, negative 2. Okay, let's see that. All right, that's a little better. Okay, so now these are green. Okay, everything in set is green. So the only thing that is left is the contains on foldable. So what we're gonna do is we're gonna go here and we're gonna go up, and I believe that we don't have test for foldable yet. Reveal in sidebar. Yeah, we don't. Okay, so let's just copy that part and create a new file and call it foldable suite. Paste that in, call it foldable like this, and let's just implement a foldable. So if you say okay, let's do it here. So let's say private, let's actually not make it private, doesn't really matter. Okay, so let's just say object fake foldable extends foldable of nothing, doesn't really matter. So all we need to do is we need to implement the fold. It's over here, right? So we're basically going to fake everything, right? So I'm just going to return the seed. There's no element, it's just nothing. Okay, so this is a final override def fold equals seed. Let's see if that compiles even. Okay, let's do pretending to test contains. So this is actually bad practice. Like what I'm doing right now, I just sort of want to get rid of it. Maybe I should just say that I don't want to test. I don't want to see the coverage of that method. No, I just sort of want to get rid of it. One day we're going to come back to it and actually test the contains, because I don't want to implement like a full blown list over here, just to test it. Okay, so what we're going to do is we're going to say fake foldable dot contains 1 to 3 should be false. Okay, so it's green. Let's see if code coverage actually should shut up now. Oh, almost 99.23. So probably, yeah, if it actually equals to the input. Okay, so let's make it not an object. Let's make it a class. Let's make it a case class or whatever. I'm just gonna say input, and okay, let's do integers. Let's say input, which is an integer. It's a foldable of integers, and we're just gonna apply the function to the seed and to the input, which is an integer now, like this. Should be fine, I think. Value contains is not a member of object fake foldable. Oh yeah, because it's an object now. So let's just do a new fake foldable of 1 contains 1 to 3 should be false. All right. So this is basically sort of like an entire collection. So we ended up having a pretty okay-ish implementation. So this fake foldable is actually basically something like a cell of one element, and because it's a case class, we actually don't need the new. So a cell was a 1 contains 1 to 3 should be false, and a cell was a 1 contains 1 should be true. So look at this, kind of spontaneously we actually ended up having a relatively okay-ish implementation of foldable. So let's do test C again. It should be 100%. All right, it's 100%. Really cool. Okay, so the last thing that I'm going to show you is this this tiny test for the strings. All right, so if we go to our set suite, let me actually go back like this. So we go to toString tests. So remember, everything is green now, and our code coverage is at 100%. However, if I add this one test, which is, it's still going to be green, toString should not produce any commas with leading spaces. Right? So I'm going to have a set of 1 and 0, and I'm going to do toString should not include space, comma. Okay, so this test is going to be green, right? Let's actually run it. It's going to be green, okay? But look at this. If I remove it and I change the implementation of toString, where is it? Where's our toString? Okay, if I change the implementation of toString by moving, for example, this split by comma space left with the plus actually, right? So if I just cut it out, I put it over here before this plus, like this, okay? Then our tests are still should be green. They're still green, right? And if we run the test coverage, then it's 100%, but there's a bug, right? Our test did not catch the bug even though the code coverage is at 100%. So sometimes, you know, you stumble on things like this. So there's a bug because if you do this, if you run that, it should be run now. One test failed. And it says, look what it did. Look what the toString did, right? So it didn't do like 0.1 or 0,1 or 1,0. It did an empty thing and then a comma and then a space and then a 0 and then a 1. So basically, you know, play around with it and to figure out, you know, just like as a home task, as a homework to find out what happened over here. But basically, you know, the split by commas. No, I'm not going to tell you. Just figure it out on your own. So if you revert that like that, then this test is actually going to pass. Everybody's happy, code coverage is at 100%, and we're pretty much done with the video. Oh, one little thing, remember I told you that you could actually, maybe as an exercise, maybe you could do it. Remember we were repeating this pattern match, and we're doing like, you know, if, same thing, else if, same thing, else. So all of these things, like this thing, for example, it's repeating 3 times, right? So it says over here, three selection regions, right? So it's been selected 1, 2, 3, right? So you could factor out this whole thing into a method. Maybe you could do this as an exercise. And then once you start doing it, you will run into a tiny issue, which is something that I forgot, which we never needed, but I was gonna add it for you so that it's easier. This plus over here, right? Because remember, if I collapse this, and if I collapse the set, oh, by the way, we changed it also to an abstract class, which is kind of cool. So this is a covariant set, right? So what we want to do is over here, we also want to make it, we want to keep it covariant over here, like this. It's going to make a few things easier. So let's just run the test again, just to make sure. All right, and let me commit that. Oh, actually, we added files. See, so if we do git status, git add dot. All right, so now let's go back to that. Okay, trees. Okay, so let's say binary search unbalanced. Yeah, that should be fine. And by the way, this is like video 9, but before that we had the video about the algorithmic complexity, which sort of was the video 9. But when you look at the commit history on GitHub, I just wanted to avoid that you have holes in there. Okay, so let's actually go there. Okay, so these are the commits. Also notice that between video 8 and between video 9, which is when I'm going to refresh, it's going to appear here. This is the video 9, our 3 commits. There was this updated README. So what happened there is basically I just added this image. Sorry, Homegrown collections. I just added this image. So this is the only change. Remember, I wanted to have all the changes in front of the camera, but you know, this was something really tiny and I really needed to do it. So I did it not in front of the camera. Okay, so let's look at all of these 3. Coverage, refactoring, binary search, and balance. So this was just for the coverage. So we turned a few things off, added a few tests. Super small, easy to review. Refactoring, relatively small. It looks like it's big, but basically we split out these methods into the empty and into the non-empty cases. And the binary search tree is the actual change. Actually, I'm going to zoom in a little bit. Oh, that's too much. No, it's fine. Okay, so we added the contains. We changed the fold a little bit. We changed the add, changed the remove, changed a few things over here, the string, singleton, and so on. In any case, I know that this was a relatively fast introduction to a relatively complicated topic. You know, those trees, they tend to be like a really recursive, and it's kind of hard to wrap your head around them sometimes. But you know, I hope that if you look at the code and you actually, yeah, very important, take a piece of paper and start drawing those trees. Otherwise, like if you're trying to fit this whole thing into your head without the pictures, it's going to be almost impossible. All right. In any case, I hope you liked this video. Like it if you did. Subscribe if you want to improve the developer inside you. Most importantly, take care.